It's just an unconditional jump to another address. And actually this, if this was possible, actually it isn't, this would be like just storing the value of the address we're going to jump into the instruction pointer. That's the whole idea behind the instruction pointer, because this one points to the next instruction we're going to execute. Okay, and the next instruction would be a compare instruction. And in this case, we're just seeing is the value of the lower byte in the A register equals 4, and if it's equal, we're going to set the 0 flag. And the next instruction just tests if the 0 flag is set, and if it's not set, it's going to jump to this address. It's a conditional branch we are looking here. So, of course, assembler instructions can also call subroutines, and that's this call here. This call pushes the return address, which would be the address of the instruction following to the call, onto the stack, and jumps to that address which is given here. And on the other hand, we've got return. That would just be at the end of a subroutine. That would pop the value from the stack and store it back in IP, in the instruction pointer. Well, one note on the byte order. Well, if you think about the decimal system we have got, that's big endian. And big endian just means it starts with the most significant byte, that's MSB. And if you just look at this example here, this is Motorola 68000 assembler. And what it does is it takes a big value, it's AA, BB, CC, DD, and stores it in the register D0. It loads the address 100 into the address register 0, and it stores the value in the first the D0 register to the pointer in A0. So if we look at the memory at this point, you can see that this is the memory address that's given here, 100, 101, and so on. And there starts our value, our first byte, the second byte, and so on. And it's stored in a way that we would write it down on our paper, like our decimal system. But there are just a few processes that do it that way, and it's most notably the Spark and the old Motorola processors, they do it. But on the other hand, modern Intel processors, they do it backwards. What they actually do is they store, this actually here is the same example as above in the Intel assembler, in Intel instructions. And you can see that it stores just the other way around. The least significant byte is in the lowest address. So, well, one can argue which is better or not. I mean, it's just a question how we look at it. So we are going to use that notation, and you will find all the addresses that are going to be pushed on the stack. They are just backwards, not like here. You cannot read them right away, so you have to well, think the other way around. Well, some notes on that, because some processors like MIPS and ARM and the new Intel processors, they're just configurable. They can do either big endian or little endian, and you can choose while you're bootstrapping. Okay, let's go into the memory model. This is a very simple segmented memory model, and actually this is very close to the model that Linux is using. And we have got the lower addresses on the top right here, and the higher addresses are right down here. And the first part of the memory is used for the so-called text segment, and the text segment contains all the instructions and all the static data. And this segment is just read-only. You cannot go there and modify the code, because that will give you segment violations. And after the text memory, the text segment, there's a data memory segment, and the data segment just holds all the global and static variables that you are defining in your C functions. And of course, it holds the heap that you can allocate by using the malloc functions. I mean, those who programmed C will probably have seen that. And at the very, very end of the memory, you will find the stack segment. And this actually is a stack where all the local variables are stored, and there's also control data, but we will see what that in the next slides. And the little arrow above here will just indicate that the stack grows towards the lower addresses. You will have to keep that in mind. So it will grow, not grow towards the end of the memory, but it will grow towards the beginning of the memory. Well, actually, there's one thing to add to this slide. You have to think about this layout. I mean, I've put some addresses right here. It's on Linux, it usually starts at 08000 and so on. And the text segment is very small, as you can see, and you've got very high values here. And this layout is actually the same for every process that you run on your system, because there's some memory management going on, and it's very important to keep in mind that you will see this situation for any process. So it looks from the view of the processes that they are all using the same memory, and that will be helping us very much when we are going to guess addresses, when we are going to need them, because they're always the same. You can expect the stack always to enter this address, and so you can make quite solid assumptions just by guessing. Okay, just as I said, the whole problem arises from the programming language C and all the derivatives, and we will go into how functions are called, and this is called the calling convention, and we will be seeing something about what a stack frame is, because that's a key point to buffer overflow. Well, I think we should see how this, what I've written down here, just actually comes. We just have a very simple C program. Okay, I hope you can see it. Can you, people in the last row, can you read what's going on there, or is it too small? Well, okay, I think that will have to suffice. Okay, what we have here, it's just a very simple program. You don't have to understand a lot. I mean, you've got a function, and it takes 3 parameters, just integer values, a, b, and c, and it returns an integer value. And what this function does, it has a local variable called d, and it just allocates a buffer of 100 bytes. And it just does a very simple operation. It just sums these parameters up and returns the value of the sum. Our main program, where the program started, it just is nothing much but declaring a value, and, well, you know what the result will be. It will store the value of 6, because it's a sum of the 3 parameters into the variable x, and it will return that variable to the shell that it's calling. It's just very simple and basic C that's going on here. And we will just now look through the debugger how this is looking in assembler. So we will just do some compiling on that. So there we are. By the way, this is not pure GDB, the debugger that comes with the new tools, but this is the Mammon extension. Well, it's called GDB Made Useful, in case you want to Googling for it. It's quite cool because it shows you the whole context that's running. You can see the value of each register that it now has. And you have a dump of the stack, and you can see the next instruction that is going to be executed. And what we see here is just how this line here looks in machine language. That actually is this part. So we can see 3 values are stored onto the stack, and we're starting with the 3rd argument. It's just the value 3. 3 is pushed onto the stack, and then 2, then 1, and then there's a call to that function. This is how all this is working right there. So we may just go through it, and if you look at this stack part here, you will see the address where the stack is pointing to. You will just find it right here, there in that register, there it is. So we will be expecting the 3 value to appear right here if we are executing the next instruction. So there it is. It just got pushed onto the stack, and just mind it's in reverse order. And the same thing will happen with the 2 and the 1. And this is our stack. We've got the 3 values on the stack, and now there will be the function call. So we will see that the execution flow is going to take place. Well, yeah, there it is. And this is how the function itself looks like. I mean, this is not, no, it's too little what we can see. So this is the whole function. You can see each function is starting with a so-called prologue, and this is the first thing that any function does. It salvages or pushes the base pointer onto the stack because it must be restored afterwards, and it makes the stack pointer the new base pointer. We are going to see how that actually works out. Might be a little confusing right now, but just let's note what's going on here. And this line is very important in the end because you can see the hexadecimal value 78, it's 100. It's just the size of the buffer we allocated. So we can see there's place reserved on the stack pointer for our buffer. And that's very important because we now learned that the buffer is going to be in the stack. So what's going on here? You can see 3 values are added to the register, and we're going to return here. And okay, this looks a little confusing right now, but we will sum up what we found here. So the function is called by pushing the 3 arguments onto the stack and the actual call of the function. And then comes the so-called prologue. That's the beginning of any function. It's just pushing the base pointer and making the stack pointer the new base pointer, and then reserving space on the stack. And for local variables, I just forgot to note it there. Well, but the epilogue, that will be the leave and the return, whereas the leave is nothing else than just the reverse of what's happening here. We just had it. It was to restore the stack pointer from the old base pointer and to pop the base pointer from the stack. It's just the reverse of what's going in the prologue. So let's just get a little graphic. I mean, that was quite a lot of numbers there. We will see what's going on. What is going on here, you can see here, that's the calling, and the last part, that's the function prologue, the function that is called. And what is happening here, we are building a so-called stack frame. And that means any function is just, well, it's just building such a stack frame. We will now see how this is working. And the situation right now is these are the pointers, and this is our stack. And the stack is growing to the left. Well, and what you can see at the right, I mean, you can't really see, it's dotted. That is just an illusion.